Peter and Mary are two astronauts. And they are both in orbit, in one and the same orbit around the Earth. This is where Peter is at this moment, at that location X. And this is where Mary is. They are in exactly the same orbit, but different satellites. They go around like this, and they are at a distance from each other, which I will express in terms of a fraction f of the total circumference, so that this arc equals f times 2 pi r. That's how far they are apart. And that means for Mary, to make it all the way back to point x would be 1 minus f times 2 pi r. So far, so good. Mary forgot her lunch. Radios Peter and says, Peter, I have no food. Peter feels very sorry for her, says, no sweat, I will throw you a ham sandwich. So Peter prepares a ham sandwich and wants to throw it to Mary, in such a way that Mary can make the catch. How can Peter possibly do this? Well, the best way, the most obvious way to do it, is to make an orbit for the ham sandwich whose orbital period is exactly the same as this time for Mary to make it back to x. And I will be more specific by giving you some numbers, then you can digest that better. Suppose they are in an orbit with a radius of 7,000 kilometers. And suppose f equals 0.05. So the separation between Peter and Mary is 2,200 kilometers. So that is f times 2 pi r. If you know the radius r, then of course the velocity of the astronauts follows immediately. You have all the tools there. So with r equals 7,000 kilometers, the astronaut, A now stands for astronauts, is a given, non-negotiable, and that is about 7.55 kilometers per second. 7.55 kilometers per second. And what is also non-negotiable is the period to go around, which is 97 minutes. All of that follows from this r. Okay, if it takes 97 minutes to go around, then 5% of 97 minutes is 5 minutes, if I round it off. So this takes 5 minutes to go. 95% of 97 minutes is 92 minutes. So for Mary to go around and go back to point x is 92 minutes. Rounded off numbers. So if I can give my sandwich an orbit which has a period of 92 minutes, I got it made. Because after 92 minutes, the sandwich will come back to x, and Mary is at x. It's important that you get that idea. If you get that idea, then all the rest will follow. So the period of the sandwich, after the throw of Peter, maybe he has to throw backwards. If that period is 92 minutes, when Mary is here, she will catch the sandwich. And so the necessary condition for this first solution, which is an obvious one, is to make the period of the sandwich, S stands for sandwich, to make that 1 minus f of the period of the astronauts in orbit. This is the 97 minutes, this is 0.95, so this is 92 minutes, and this is 92 minutes. So then Mary will be back at point x. What is the orbital period of the sandwich after the throw? Well, that is 4 pi squared. You can find that equation number 6 times a to the third divided by mg to the power 1/2. That must be equal 1 minus f times the orbital period of the astronauts who were in circular orbit. So I take equation number 1, so that is 4 pi squared r cubed divided by gm to the power 1/2. That is a necessary condition. Look, we lose m, we lose g, we lose 4, we lose pi. What don't we lose? Well, what we don't lose is a to the power 3/2 equals 1 minus f times r to the power 3/2. So a equals r times 1 minus f to the power 2/3. And this is an amazingly simple result. It means if you know the orbit of Peter and Mary, which is r, and if you know how far the two lovers are apart, which is expressed in this f, then you know what the semi-major axis is of the sandwich orbit. That comes immediately out of this equation. But once you know the semi-major axis, you can immediately calculate with equation 5 the speed of the sandwich. Because if equation number 5 will tell you that minus mmg divided by 2a, a being now the semi-major axis of the sandwich orbit, equals 1/2 m times the velocity of the sandwich squared. This happens at location x after the burn. After the burn means after Peter has thrown, minus mmg divided by capital R. Because the sandwich is still at location capital R, but Peter has changed the speed to Vs. And so once you know A, this equation immediately gives you Vs. And once you know Vs, then you know with what speed Peter should throw. Well, let us work it out in detail in the example that we have there. If we calculate A with the numbers that we have there, which you can easily confirm, because you can apply this equation for yourself, you know what F is, you know what R is, then I find that A is 6,765 kilometers. Notice that this is smaller than R. It better be, because it's clear that after the sandwich is thrown, that we get a green ellipse. We want this time to go around to be less time than Peter to go around. And if this time is less than the time that it takes to Peter to go around, he has to throw the sandwich backwards, and therefore you expect that the semi-major axis will be smaller than R. And it is. The speed of the sandwich, which follows then from equation number 6, which was the conservation of mechanical energy, is 7.42 kilometers per second. Now, what matters is not so much what the speed of the sandwich is, but what matters for Peter is what is the speed that he will have to give the sandwich, which is v of s minus v of a, and that you have to subtract the speed. V of s is the speed of the sandwich, v of a is the speed of the astronauts in orbit. This is minus 0.13 kilometers per second. And the minus sign indicates that he has to throw the sandwich backwards. So, quite amazing. He is seeing Mary all the way in the distance, and in order to get the sandwich to Mary, he doesn't do this, but he does this. And the sandwich then will go into this new orbit, going still forward. 92 minutes later it's here, and Mary, where we were here. So he goes forward, 92 minutes later the sandwich is here, 92 minutes later Mary is right at that point and can make the catch. Now 0.13 kilometers per second is 300 miles per hour, which is a little tough, even for Peter. And so we have to look for different solutions. This won't work. This was an easy one, but it doesn't work. Well, there is no reason to rush. We can make the sandwich go around the Earth 2 times, and Mary 3 times, or Mary 2 times, and the sandwich only once. As long as they meet at point X, there is no problem. So we have a whole family of solutions. we can have Mary pass that point X n a times, and we can have the sandwich pass that point X and sandwich times. As long as these are integers, that's perfectly fine. Then ultimately, if they have enough patience, they will meet at point X. And if you take this new concept into account, that you can wait a certain number of passages through X, then the equation that you see there, the relation between A and R, changes only slightly. You now get that A equals R times n of A minus F divided by ns to the power 2/3. And if you substitute in here a 1 and a 1, which is the case that they make the catch right away, then you see indeed you get R 1 minus F to the power 3/2. So that's exactly what you have there. Not all solutions that you try will work. One solution that won't work is NA equals 1 and NS equals 3 has no solution. And I'll leave you with the thought why that is the case. Has no solution. In 1990, when I lectured 801 for the first time, I asked my friend and colleague George Clark to write a program so that I could show the class this toss of the sandwich, with Mary and Peter in orbit, and the sandwich orbit, and everything, and the catch. And he did. It was a wonderful program, but that program no longer works, because that's called progress, the computers have changed, and so my right hand, Dave Pooley, offered to rewrite the program so that it works on Athena. And we were going to demonstrate it to you, and you can play with it yourself. It is available on the homepage, so whatever Dave is going to show you, you can do yourself. The input parameters that we need for this program are the radius r, our f, and our n of a, and our n of s. And the program will do all the rest. So you can specify how many times you want Mary to go through point X, how many times you want the sandwich to go through point X. The program will then calculate for you the speed of the sandwich. It will also give you Vs minus Va, which is really the speed with which Peter has to throw it. But very cleverly, the program works with a dimensionless parameter, which is this value. And this value, which is Vs divided by Va minus 1, is a number that is quite unique, because you get solutions which turn out to be independent of capital G and independent of capital M. And I'll give you an example. Suppose you will find for this dimensionless number, suppose you find minus 0.0175, which is the solution for n1, na is 1, and for ns is 1. So you'll see that. The computer will generate that number for us. If now we take our orbit for 7,000 kilometers, we know what V of A is, and so we can calculate now that Vs minus Va is the Va times that number, but we know what the Va is 7.5. So you get minus 0.175 times 7.55 kilometers, and lo and behold, that is our minus 0.13 kilometers per second. Of course, it has to be that number, because that's what we calculated for our case, n equals 1. There it is. And so this dimensionless number is very transparent, and we will show you some examples. This would be the 300 miles per hour, which of course is not very doable.